Hey everybody, we're going to start getting into the Congruent Triangles chapter. This is the chapter that has the most proof in it. It's not going to be your favorite, but by the end of the chapter, I think you will understand proofs a whole lot better. And once we get through it, we can move on to bigger and better things. So, I want you to look down just at this picture, for example. And we can give it letters. We can just call this triangle ABC. So that triangle on the left is triangle ABC, which, by the way, if you were to name this triangle officially in geometry terms, you would just use a little teeny triangle symbol and you would call it triangle ABC. Okay, that's all you need to do. Now, if we were to look at the triangle on the right, you could name it the same way. Now, if we want to follow sort of the same pathway, as we did on the left, we could just say, well, this would be ABC, so then this would be DBC. Now, if you're just giving it a name, order doesn't matter. But if you're trying to prove a point, order does matter. So I just want to warn you before we get into the lesson. But let's just do that. All right, triangle DBC. So again, you can name it in any order you want, but we're going to see later that we're going to be matching things up. We're going to have to match the pieces that are alike, and so when we do that, the order is going to matter. But I think I'm jumping a little bit ahead of myself. So if you want to prove that the two triangles down below are the exact same triangle, spoiler alert, they are. Would you have to check all three sides? Would you have to measure all three angles? Would you have to get a protractor out? And the answer is no. First of all, most of you don't even carry protractors with you. Second of all, it would be a waste of time. And here's why. If the three sides of a triangle are congruent, the angles are too. Okay, there's a rule that says that as well, and that's what we're going to cover first. Postulate 4.1. This is chapter 4 in the old book. The very first postulate says, if the three sides of one triangle are congruent to the three sides of another triangle, then the two triangles are exactly the same. The two triangles are congruent themselves. So basically, if you know that the three sides match up, that means the triangles are exactly the same. It means the angles will also match up. It means everything will be the same. Now, this is called, because we are just so creative in math class, the side-side-side postulate. Now, normally I don't let you abbreviate, but because this is used so much in geometry, everybody in geometry pretty much agrees that if the three sides match, then your triangles are congruent to each other. So we just abbreviate it SSS. Okay. So more or less, if we look down at this picture here, we start with side AB right up here. There you go. There's side AB. That didn't come out very thick. Let's do that right there. All right. If you look, side AB has the exact same marking as side BD. So we could say that segment AB and segment BD are congruent. Well, that wasn't what I was looking for at all. So side AB and side BD are congruent. So let's just put a little congruent symbol in there and make sure we're talking about segments here. There you go. So you could say that about AB and BD. Now, if you look, you can also take a look at this picture right here. The bottom part of this picture, you've got AC and DC. Not a coincidence. I am a fan. So AC would be congruent to DC. Now, we've got one last piece of the puzzle as far as the sides are concerned. We have one side here that is shared with both of them. So basically, you've got BC and you've got BC. Now, when it comes to BC and BC, that seems kind of weird. How do we know that they are congruent? Well, they're the same thing. Now, in the last chapter, we talked a lot about the transitive property. In this chapter, we're going to talk a lot about the reflexive property. And the reflexive property was, long story short, you are congruent to yourself. If you have a side that is shared on two triangles, then you are congruent to yourself. That's how this thing works. So we have side AB matching with side BD. We have side AC matching with side DC. And we have BC matching with BC because you are congruent to yourself. So what that leaves us with is a final statement. Because the three sides match, that means the angles do too. And we could just say, hey, look, these two triangles are congruent. So triangle ABC is congruent to triangle DBC. That would be a congruence statement. Okay. You're not going to be great at those right away, but that's what it should look like when it's all said and done. Now I'm going to move up. Now, there are actually a lot of different ways to prove that triangles are congruent to each other. But the next question is, what would happen if we were only given two sides? Would there still be a way to prove that two triangles match up? Now, the picture down below would be the best example of this. I can tell you right now that these two triangles match up with each other. These two triangles are exactly the same triangle. Yes, one is sort of a reverse reflected version of the other. It's sort of rotated around a little bit, but they are still congruent. And the way I know is because of one of the angles in between. You can still prove that two triangles are congruent as long as the angle in between the sides is congruent. So let's look at this picture, and I'm just going to give it some new names here. We already used A, B, C, D, so let's use J, K, L, M, N. Let's do it that way. So here's the deal. If you look over here at point L, you have two angles here in the middle. Now, I don't know what these angles are, but I do know that they're the same because they're vertical angles to each other. Okay, and what that leaves us with is a matching side, another matching side, and then the angle in between. And that is actually the second rule. If two sides and the included angle, included means it's the angle in between the two sides. If two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the two triangles are congruent. Now, the key here in the name is going to be to follow my arrow. We have a matching side, then we have a matching angle, and then we have another matching side. So the way you would have to name this would be the side, angle, side postulate. Now again, we have talked in math class about how we're not very creative with names, but in this particular case, they are being creative enough to let us abbreviate because it comes up that much in geometry class. So when you use that abbreviation, everyone will know what you're talking about in the geometry world. So it actually turns out in this picture over here, we do have enough information to prove that the two triangles are congruent because we have a matching side from here to here to go along with from here to here. So basically, NL and KL match. Then we have an angle right here in the middle that matches. And then we have another side that goes here and here. Now, remember what I said about order. Order matters. You have to make sure you're following the same pathway. In this case, what you would find out, if you went from, we started with J to L. So we're going to say triangle JLK. Okay, so we're going to follow that pathway. We're going to follow J to L to K. If you wanted to make it match on the other side, you would have to follow the pathway from M to L first, because you want to make sure that you're going along the pathway that has the same markings. So now you'll do M, L, N. Okay, because we have a matching side from here to here that goes along with the one from here to here. Then we have the angles. And then we have from L to K matches with from L to N. And that statement would be true because of side, angle, side. All right, now a couple quick examples. Is there enough information to prove these two triangles are congruent? If the answer is yes, state the postulate you would use to prove it. So I'm going over here, and we have a matching side here and here. We have another matching side here and here. Does the third side match? In this case, the answer is yes, the third side matches because it is shared throughout both of the triangles. Now, we do need to check the order. X, Y, W. So it goes across the part with two markings, and then it goes down the middle. Z, W, Y goes across two markings, and then down the middle. It checks out. The statement works. The answer is yes, they are congruent, and the postulate that we would use to prove it would be the side-side-side postulate. All right, now let's go to the next one here. You've got, oh, I didn't actually say yes. I should probably say yes. Okay. Now, this next one, we're actually going to go to the third one because the third one turns out also to be yes, but for a different reason. This time around, if you follow the order D, K, A, so D starts here, and then we follow along the side that has one marking, then we hit the angle that's marked, and then we go to the side that has two markings. Now, if you were to look over here at TKS, then you've got one marking, the angle, and two markings. Sure enough, they check out. So the answer would be yes, and in this case, the reason why it would be yes would be because we have two sides and then the angle in between this time. So this time, instead of side, 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 it would be side, angle, side. Okay. Now, the third picture, the second picture I'm saving for third. The reason is there's a reason why this is not going to work. MAE would kind of follow that pathway. TAE would kind of follow that pathway. And we do have a shared side in the middle. The catch is our rule. Our rule says two sides and the included angle. Long story short, it means the angle that you have to use is the one in between the two sides. So if they had given me this and this, the answer would have been yes. But the angle they gave me is not the included angle. It's the angle that's out in outer space over there, which means the answer to this question would be no. if you want to have a good laugh, you start working your way through, you think about it, and it's like, well, this is an angle, this is a side, this is a side. Yeah, that would definitely be the angle side-side postulate, which does not exist, and it's a little bit inappropriate. But that's another story for another day. All right. Hope this helps. I'll see you next time.